So I hope you got some rest. So now we can attack this problem again. So as you remember, we are done with the base case. So this is the statement we want to prove. We want to show that for any bivalent set of processes from some configuration, I can make it bivalent for just a couple out of them. Just choose two out of them and make it bivalent from some extension of this configuration. And make the rest of the processes poised while covering some distinct memory locations. So notice that if I do it for n, if I have initially a set of n processes, all processes are performing steps, then I already cover n minus 2, which is almost what I want. Almost. Okay? So this is actually my goal, is to establish n minus 2 covering and maintain this bivalency thing. Okay? And the base case, well, is it sounds a bit stupid, but the fact is that I need this precondition. I need some bivalent configuration to start with. Because the precondition is if there exists a bivalent configuration, then this is the case. So I need to find some configuration in which two processes are bivalent. Otherwise, there's nothing to prove because nothing is bivalent. So this is what I'm doing here. I'm finding some initial configuration C0. This is my initial configuration where nobody took any steps whatsoever. And in this configuration, one process has input 0 and the other process has input 1. And I only consider these two processes P and Q. Okay, so I let P run solo, it should decide 0. Let Q run solo, it should decide 1. Of course, this initial configuration is by definition bivalent for these two processes. Okay? Beg your pardon? Alpha is the schedule. Alpha, the Greek letters are always schedules here. Except for one special case where I use delta and it's just a singleton schedule, just one step. Okay, and capital letters are either sets of processes or configurations. Well, I think I only use C here for configurations, or C prime, whatever. Okay, and C extended with alpha, it's also a configuration. Okay. Right. So induction step. And now it's this is why I put these things on the whiteboard, because I'm going to use them extensively. So let's imagine that we have a set of 3 or more processes, which is bivalent from C. I want to prove it by induction. I assume already that for all smaller sets of size cardinality P minus 1 or less, the claim holds. Okay? So now I take some set of 3 or more. I already know that it holds for 2. Okay. So by lemma 1, the first thing I do, I extend it to some another configuration in which a proper subset of this process P is bivalent. Remember that lemma 1 is doing exactly this. And I fix this process Z, and I'm going to use it at the end of the construction. I'm not touching it for now. So I reduce the set of processes P by 1. And still have bivalency. Okay, this is my first step. So I have some configuration D, which is C extended by this gamma, which is some extension. Well, I use phi here, but I use gamma here. Doesn't matter. Okay. Now I use the induction hypothesis, because now I have strictly less number of processes. I have cardinality of phi minus 1. And I know that I can extend it now using the induction hypothesis to some configuration D0, which is an extension of D. And I can find a pair of processes Q0, which is a subset of this. You know that the P is of size 3 or more, that such a pair exists. Okay? Such that Q0 is bivalent from D0, this is by induction, by the hypothesis, not, and all the rest, which is P minus Z minus Q0, cover distinct registers in D0. Okay? So far so good? I just use the induction hypothesis on the sizes of the set, cardinality P minus 1. Okay, so this is my first configuration. Now, you can see that I use 0, so which means that I'm going to extend it. Okay? So far, so good? So this is what I did so far. So I started with the bivalent. I run up to D, and I get some configuration which is bivalent, but the set is strictly less. I take Z, put it aside. I'm going to use it later. Then I use the induction hypothesis. Here I use lemma 1. Here I use the induction hypothesis to show that, okay, actually I factor out a pair of processes P and Q out of this set P minus Z. And in this extension, I have this set of processes P and Q is bivalent, okay? And the rest, which is P minus PQ minus Z, cover distinct registers. And remember, if P is already only 3, size 3, then this is empty. Yeah, I don't have to cover anything. Okay? Good. So now I'm going to use this lemma 3. How I use lemma 3? So what I do, I already have a covering block right, yeah, which is defined here. This is a block right. I can use it, yeah, because you see in lemma 3 I have a bivalent configuration from C, and there is some block right by a disjoint set of processes, and this is exactly the case here. Yeah, so you have P and Q, which is bivalent, and there is a disjoint set P minus PQ minus Z, which cover distinct registers. This is what I'm going to use. Okay, so this is my block right beta I. So now I actually do induction step. Yeah, I already have the initial state. Now I go by induction from DI to DI plus 1. I have this DI already fixed. Yeah, I use lemma 3. Yeah, which is phi I. Well, phi I, which is I use here, and beta I, which is a block right by this process P minus Q minus Z. Yeah. What I get by lemma 3 is that this union for some Q in this set Q is bivalent. Okay? So I just use, well, you need to make an effort and change a little bit the letters, which I use here and here, but this is the same statement. Yeah, I start from one bivalent configuration DI, I apply lemma 3, and I get a strictly different subset of processes, which is bivalent now. Okay? And they cover, so this is what I do. And finally, well, I have this set, which is bivalent. Yeah, notice that this set, again, has a strictly less cardinality than P. Okay? Yeah, because I took a pair from P, took a process from P, added another process, the cardinality is P minus 2. Yeah, and I know that by induction, what I can do is I apply again the induction hypothesis and get a new configuration DI plus 1 such that there is a pair of processes in this set, which is bivalent. I have the rest, which is P minus P prime Q prime minus Z covering distinct registers. Okay? So and then I can use it over and over again. So I use the lemma 3, I use the hypothesis, and I go from DI plus 1 to DI plus 2, from DI plus 2 to DI plus 3, and so on. So I can continue this forever. So I can longer and longer bivalent extensions of the initial configuration C0. Okay, so this is my, well, initial configuration C, I should say. Yeah, C. C0 was there for only 2 processes. Okay, so what is the takeaway from here? I have a longer series of bivalent configurations for different pairs of processes, yeah, in which different subsets of registers are covered, possibly different, possibly the same. If the same, I'm happy. But if they are different, I'm not that happy. However, the space of registers I'm going to use is finite. Well, if it's already infinite, I'm done, because I was looking for space bound for consensus. If I use infinite number of registers, I'm very happy. You have an algorithm which is unbounded. So let's, to be non-trivial, assume that it's finite. And I have a series of configurations, DI, DI plus 1, DI plus 2, in which subsets of this finite set of registers are covered. Okay? But the set of registers which I have in my disposal is finite, which means that there must be two configurations in this series which cover exactly the same set of registers. Okay, because a finite subset, a finite set can only have finite number of subsets of size actually p minus 2 or p minus 3, sorry. Okay? So there must be two configurations which are bivalent in which the same set of registers is covered. Okay? And let's call them di and dj. Okay? So they cover the same set of registers, well, let's call them S, I don't know, and this of size p minus 3. Okay? So this is what I have. So I started with C, my initial bivalent configuration. I extended to D, where I took out some process Z. And then I start marching through these configurations, and I reach some DI here. Well, then there's DI plus 1, blah, blah, blah. And then I reach DJ. Okay, so you have two configurations, DI and DJ, in which some pair of processes QI is bivalent, and then P minus Z minus QI cover some set of registers S. Then I have some configuration DJ in which some process, possibly different set of processes QJ is bivalent, but the set of covered registers is against S. Okay? And this is the moment when I'm going to use Z. So I put it aside, now I bring it back. So I have some process in addition, which I can use. I never used it so far. Yeah. Z, I only used it up to here, and then I didn't use it. So these executions here do not involve Z at all. Which means I can start it, I can introduce it somehow. And actually, the place I'm going to introduce it is somewhere here between DI and DI plus 1. Okay. So now what we're gonna do, we're gonna zoom into this particular step. Okay, we run Z from DI phi. Remember that phi is this guy here, which I used to reach the block right. So I run it, and the claim here that Z must cover something which was not covered in S, which is not part of S. Okay? How do I know this? Well, otherwise, if it's covered and I run it until it decides, yeah, I just use what we had this lemma 2. That decides something, but there is an extension which is bivalent, and I lose the decision. Because I decide something, I wrote to some registers which are covered, which are elements of S, which are overwritten by this beta I, which is after phi. Yeah, this is the block right on S. Yeah, remember that this is our our initial assumption was that, yeah. So there is this DI which is in which these elements of S are covered. Yeah, so I cannot actually. I cannot I cannot see the difference if I only write to S. Okay. Okay. So this is where I use this lemma 2, which actually you're supposed to prove as an exercise. But lemma 2 is almost trivial. You can see that. Okay. So this is what I'm doing. This is phi. This is the block right bi, beta I. Sorry. By some set Ri, it doesn't matter. I'm not sure I use anywhere this Ri. I use QI. QI is this set of processes, the pair of processes QI. This is my zeta, which I use here. And I run this process Z running solo until it's about to write somewhere outside of set S. Okay, remember that this set S sometime later is also covered by some other configuration DI plus 1, DJ. Okay? But I stop it just before it writes. So it is about to write to some register outside of S, but I stop it here. And then I run as I ran before, because this guy didn't write to anything outside of S, which means that I can cover anything with this block right. Can extend it with Psi and reach DI plus 1 prime now, because it's a different configuration. Now, the difference between DI plus 1 and DI plus 1 prime is that here Z made some steps. Yeah, so it performed some steps, so there is some difference, but nobody sees it except for Z. Okay, because all writes which Z performed are hidden, are covered. Okay? And then I continue. So now I have di plus 1 prime, di plus 2 prime, di plus 3 prime, up to dj prime, which is exactly the same as dj except for the local state of Z. So which means that nobody else, no other process other than Z, can see the difference between dj prime and dj. And remember that in dj, we cover all these registers S. And now we bring Z. Z actually covers something outside of S. So now we have dj prime, a bivalent configuration for some set qj for two processes. And all the rest are covering, well, one more process. So we covered S plus one more process. And this is exactly what we need by induction. Yeah, so this is my dj. PQ is bivalent from dj. This is what we used to call qj. Well, some pair of processes for which we constructed by induction. P minus PQ cover S. Yeah. In addition, there is another process Z which is covering one more process. Yeah. And we are done. Yeah. So we have constructed the induction, and we need one more step because now if we take P of size n, we covered n minus 2 registers. Our goal is to cover n minus 1. Yeah? And then n minus 1, we need one more step, and this is what we do here. Yeah? So we assume that there is some run from dj because it's bivalent in which PQ, everybody but PQ decides V. Yeah. There is some execution because it's some execution in which everybody else but PQ decides some value. Let's this value be V. Since dj prime is bivalent, there is bivalent for PQ. There is an extension by PQ only in which S is written and decide 1 minus V. Yeah. If these guys, if these guys here do not write anything outside of S, then it's going to be absolutely indistinguishable. So, which means that something outside of S should be covered, should be written, and as a result, we get n minus 1, and then we are done. Okay, so there's a little bit of discrepancy. We established the lower bound of n minus 1 registers, but in fact, the algorithms, for consensus, all algorithms are using n registers. So it's a little bit annoying, and I think this was fixed later by if I remember well, Lekejou and Arati Gelashvili in some paper. But it's not the point here. Again, so I want to emphasize that let's focus not on the result but on the technique. Yeah, so we talk about techniques. There are so many lower bound results, but considerably less techniques which are used in these results. And if we master a technique, we can apply it in a different context. And this is the goal for us. And we want to master a technique. And the technique here is a combination of valency and covering. Okay? So n minus 1 distinct registers are used. Perfectly, we're done. And again, I would encourage you, I put in the folder, which I put in the link to these slides, there are slides. There's a list of literature, like the bibliography of list of papers which you might want to read if you want to understand more about this topic. And there are some papers which I also published, papers which I mentioned here, in particular this paper by Lekejou. So you might want, it's a very short paper, you might want to have a look at it. If you want to come back to this argument. But essentially, I presented you the argument, but if you really want to understand every little detail in it, you might want to look at the paper. Okay, so we wrap up concerning covering and valency. We come to a different topic now. So what do we know about covering? Yeah, without valency so far. We talk about perturbable objects which can be perturbed by inserting some operation so that the result of another operation is perturbed. It should be different. Yeah, these are counters, compare and swap, atomic snapshots, and so on. If you want to implement them, we need linear space complexity for that. And we use linear step complexity in the solo run. Yeah, so this perturbed process should take linear number of steps before completing an operation. Okay. well, consensus is not a perturbed object, actually. It's an interesting observation. So consensus does not fall into this category. So that means we cannot actually use this proof for consensus. Consensus, if some process decided, at some point the decision is fixed. There's no perturbation. You cannot really change it. So it's a very interesting object in a way. So that's why for consensus, for one-shot non-perturbable consensus, we use additional tricks related to valency. We can only use space, but there's a conjecture that it also holds for time, but no proof. So if you're interested, you can try to attack this problem. Okay. All these proofs are based on constructing a run, a specific execution, which is worst case. So we look for a run in which something bad happens, or a lot of resources are used, or a lot of steps are taken. Okay, so it's always a worst case construction. So which some people would say, oh, well, who cares? Well, especially not for space. For space, of course, in the worst case, if we have exhaust the space, the algorithm breaks. But for time, they would say, well, worst case analysis for time bounds is irrelevant. Why? Because they would say, it rarely happens. So your worst case executions never happen. Well, statistically, it's negligible. Very rare case in which you have this particular execution. And to be honest, I don't have much to say against it. Yeah, it's true. Maybe in practice it doesn't really matter. In practice, maybe the average case matters. In average, how much time you spend, or throughput. In average, how much time it takes, how many operations you can execute in a second. Yeah, maybe that's more important. I have no opinion on this. Again, I want to insist. We talk about techniques. We don't talk about practice so far. Okay, and now for something completely different. So the thing is that we do not go to worst case executions anymore. So we take a different approach, an approach which is based on a holistic argument. What is a holistic argument? It's like you take all executions of your algorithm as a whole, or maybe a non-trivial set of executions of your algorithm as a whole. And you look at all these executions and try to deduce properties of your algorithm from this whole set of executions. And this is where some information theory is going to help us. Very little, actually. It's very basic. I'm sure you all know this. Okay. So we talk about a specific paper, which is written by Rui Fan and Nancy Lynch. And this is matching lower bound, or sort of matching lower bound to the algorithm by Young and Anderson, which Danny Hender mentioned. If you remember, if you talk about mutual exclusion, very first class in this summer school, he discussed the Peterson algorithm for two processes. And the algorithm had constant complexity. It's both space and time. Okay? Well, again, when we talk about time, we should be careful. When we talk about mutual exclusion, there's a lot of spinning. You don't count spinning. Spinning means you wait for some variable to change. You don't count it because it's unbounded. You cannot count it. Instead, what you count is a moment when you perform the change. And what Danny called remote memory references, which matters for consistency models, which are realistic with caches. Either as you have cache coherence or you have distributed DSM, distributed shared memory, where you have distinction between local operations which are negligible and remote operations which you should count as a complexity measure. Okay. Then he took this Peterson algorithm and formed a tournament tree. Yeah. So what is a tournament tree? So you split processes in pairs. Yeah, you join your pair, try to win against your competitor. If you win, go further. You win against the winner from another pair, and so on, and further and further and further. So since the complexity of well, now we talk about the work. Now it's more related to time. The RMR complexity, remote memory reference complexity, for a fork in a tree is constant. You go through log n. For n is the number of the size of the system. You go through log n competitions, and you're done. So the RMR complexity per process is log n. Total RMR complexity for n processes each entering the critical section is n log n. Okay, so there's an algorithm by Young and Anderson which has O, big O of n log n total work. This is called total work. Yes. No. Again, if you look for everybody, so this is a total work. So the cost of mutual exclusion, we talk about total work. Yeah, total work is the metric. Total work is the amount of remote memory references which all n processes should to execute if each of them wants to enter the critical section. If you take the tree, each process should lift up across the tree and reach the top. Yeah, so we have n processes. Each process takes log n RMRs. Total number of RMRs in this particular execution is n log n. Yeah. Okay. Yeah. So we consider a set of executions in which everybody should be served. And so this is important. Yeah. So we don't zoom on any particular process. We take all of them and count how much work they all did. That's why it's called total work. Yeah. So this was an upper bound, and yeah. Well, I think it's more like log n rather than n, because you compete, you go through the tree, and in each competition you just do something. Yeah. Mm-hmm. Yeah. Mm-hmm. Yeah, but you wait. What you count is not only your write operations, but also what the RMRs. RMR is you spin until this particular lock is released. Yeah, it's a lock. Yeah, the element in the tree is a two process Peterson's lock. So you need to pass through the exit section. You spin until it's released, and then you go. Yeah, and this to get released is to execute one RMR. Yeah, so you have to, before you reach the top, you have to execute a log n RMRs. Yeah, okay. Right. So, but I need to make a remark here. So this looks like a lower bound matching the Young and Anderson upper bound, but it's a simpler result. So they didn't consider what we call a realistic cache coherence or DSM model. They considered an abstract model which they called state change. And their follow-up papers, and actually I think the most important among them is Dani's paper with Hagit Atiye and Philip Wolfel, where they actually make it more realistic, but they use the same argument. And again, what I focus here is not the result, but the argument. And the first idea, the first paper in which this idea of using information theory was coined was this one. And it's beautiful. It's technical, but it's very impressive. So again, we talk about some abstract model in which mutual exclusion is solved. And what we count in this model is what they call state change operations. So essentially, if you took any, okay, so now I don't need this anymore, I can remove. So any mutual exclusion algorithm involves some waiting. Yeah, so you wait until something happens, otherwise you cannot do it. Yeah, we know that mutual exclusion cannot be done wait-free. Yeah, it sounds stupid, wait-free mutual exclusion, because a process in the critical section blocks everybody. Yeah, so everybody should wait until this guy leaves. Yeah, so whenever you have a wait statement of this kind, wait until x is 0 or whatever, yeah, or not 0. Yeah. So this kind of statements means that you read x, and then you spin. For example, if it's a cache coherent model, you spin on your local cache until it's invalidated. As soon as it's invalidated, it means that you need to perform an RMR. You need to go to the memory and fetch the up-to-date value. Yeah. So what you count is this exactly this step where you change your local state, you change your local variable, and this is what you count. And this is what's counted in this paper. But they didn't really look into actual details of a consistency model of your memory. So they simplified it a little bit, which is okay, I think, for as a first approximation. Then there are other people who made it precise. Okay, so let's can we switch back? Well, imagine the cache coherence model. Yeah, you have a copy where you read it once, and then you keep spinning on your local copy until it's invalidated by the cache coherence protocol. And it's invalidated because someone has written to it. And this is an RMR. Then you have to go to the memory. Yeah. So if you just count spinning, it's useless. It's not a good metric because it's unbounded, of course. We have asynchronous protocol, asynchronous model. Okay. So what is the result? So they say that the total work of any n-process mutual exclusion algorithm, and it's only deadlock free, you don't even need starvation free for that, is omega of n log n. Okay, the total number of operations which you need to perform to serve every process in the set of n is n log n. In terms of RMRs, but what they call here in the paper is state change operations. State change is either a write or a read, which is non-trivial, which is non-spinning. Okay. And so, as I said, this was from POTC 2006, if I remember well, the Fan and Lynch, and the 2 years after, Atiyah Handler and Wolfel proved it for real stuff. Yeah. I should say probably that, I don't know, DSM memory, I'm not sure it's used any longer, but at the time there were a competition. Well, there were many machines which used this particular consistency model. Now I think it's mostly cache coherent as a more advanced, but still I think it's interesting to see if there are some interesting distinction between the two. Okay, and as I say, it's tight. Yeah, so we have a Young and Anderson algorithm. And it actually holds even for stronger primitives. You're not restricted to reads and writes. Yeah, you have compare and swaps. You can use compare and swaps and still the lower bound would hold. Okay, so unlike consensus, for consensus, if you have a compare and swap variable, you're done. Yeah, you do it in one step. Yeah. Okay, well, mutual exclusion, you already know what it is. Yeah, you have to know two processes are in the critical sections at the same time. And we're only interested in deadlock freedom. If there is some guy in the trying section, yeah, so you pass through trying section, go to critical section, then exit section, and we never come back. We don't care. In this particular work, we only assume that every process accesses critical section once. You have a resource, everybody grabs the resource, releases it, the other grabs the resource, releases it, and so on. So until n processes are served. And if at least one process is in trying section here, then eventually some process will get to the trying section, to the critical section. Not necessarily the guy who is. But if everybody is doing this once, it's the same as starvation freedom, because you only get to the critical section once. You release and you don't touch the critical section anymore. Another guy enters, so eventually everybody is served. Of course, we need to assume some non-trivial things about the behavior of the processes. For example, you're not allowed to block in the critical section or in the trying section or in the exit section. Yeah, so you should follow the protocol. Okay, so if you're interested in this particular topic, you should go to the lecture given by Nir Shavit at 2 years back at this summer school, and he gave like a beautiful lecture about different protocols implementing mutual exclusion with all kinds of optimizations. Okay. Well, just to give an example of protocol, I am not talking about Young and Anderson. This is a classical protocol. So we discussed two processes, Peterson. This is n process. Actually, Peterson didn't think about trees. He gave a much simpler protocol. He gave a protocol which is using some kind of waiting rooms. I have n processes, and you have n waiting rooms, and in each room, at least one guy is left behind waiting. Since you pass through n-1 rooms, and in each room at least one guy left waiting, at most one guy enters, actually exactly one guy enters the critical section at the end. And then it comes back and releases the guys waiting and so on. So it's a very interesting protocol. but very expensive. So it's not the optimal whatsoever. Yes. Good question. Why do we need n log n with cas? I need to look back at the paper, but if I remember well, it's still the case. You can think of an algorithm which does it faster with cas. Let me think about it. I don't know. That's what I read in the paper and I trusted them, but I need to look back again. It's a good question. Okay, so what I wanted to illustrate here is that you have this waiting phase here, and this is where you're blocked in some room, which is M in this case. You wait until some guy is waiting instead of you, or there exists there's no guy which is ahead of you in the waiting rooms. You got the answer. Okay, so you tell me the answer after the class. Okay. Sorry, I just this is not the topic of this, but we can discuss it after. Of course. Okay. Another exercise. What is the total work of this algorithm? N square. Well, prove it. And actually, it's interesting to prove it for both models, for cache coherence and DSM, because again, DSM is a bit special because you need to assign variables to processes, and so it's so it's not n log n. So it's suboptimal if you want. Okay. What is the idea of this? The idea is so if you want to enter the critical section, you need to compete. Well, you have n processes. You compete against n processes around. Yeah. What is computation? Well, in general, computation is about accumulating information. And it's especially the case for distributed computations. You take steps of your algorithm. You learn more about the other processes. You compete with them. You write them somewhere. You read what some other processes did. You acquire some information. What kind of information you want to acquire in a mutual exclusion algorithm? This is information about the guys who are served, who you're not competing with, the guys who finished their critical sections. Why do you need this? Because you have the critical, the mutual exclusion property. Yeah? You cannot enter the critical section before someone else left it. Okay, so you need to get an indication. Every guy who entered the critical section so far should causally precede you. Yeah, before you enter your critical section, you need to get some causal chain of events which tells you that this guy has left. Okay, so this kind of information. So intuitively, you need to learn something about the prefix of critical sections preceding you. You don't care about the guys who enter the critical section after you, but you need to know something which is before you. Okay? And this kind of acquisition of information incurs some costs. Yeah. So, okay, so as I said, we only focus on canonical executions. This is called canonical, I don't know why. Executions in which everybody enters the critical section once, and that's it. Okay, everybody enters, everybody leaves. So the processes, in some cumulative way, in some abstract way, they should learn about the order of critical sections. If you happen to be the first one, you don't care. You don't care about the others. But if you happen to be the last one, you should know about the order of all critical sections before you. Okay? Not only the fact that everybody left, we should know that everybody transitively through the other processes. Okay? So again, the intuition is to getting C bits of information about the order. It's not a theorem. I'm not going to prove it now, but it's just the intuition. Earning C bits of information about the order of steps, the order of critical sections, somehow it's C work, C number of RMRs, if you want. Okay, so this is one of the things to be proved. How many orders we have? N factorial. All permutations of processes. What's the best encoding of a set of an element in the set of n factorial? N log n. Yeah, because n well, asymptotically n factorial is n to the power of n. And this is the place, this is the only place we use information theory here. Shannon tells us the number of bits you need to encode an element in the set of n factorial is log cardinality of the set, which is n log n. Okay? This is where n log n comes from. Okay? So remember in the second class given by Eli Gaffney, there was an approach of modeling all executions in the system as what we call a simplicial complex. It's like some structure where every simplex, every element of this complex is a specific execution. All executions are glued together through this interesting combination of vertices and edges. And you see, you can somehow look in all the set of possible executions and see them visually. Okay? So here, instead of using this combinatorial approach, what we do, we use information theoretic approach. We take all possible executions and we encode them. We create a code book. So each execution in the set, well, I'm not talking all possible sets. I just take subset of executions in which different orders of critical sections are observed. And for each such execution, I give a code word, yeah, which encodes this information somehow. And by taking all these executions together, what I get is a code book, yeah, a set of codes for different executions. Since you have at least n factorial such executions, the code book should involve at least one string of a length n log n. Okay? And this is it. Well, not yet, but this is the idea. So here, first thing about the visibility, what I said, you should be able to see who was in the critical section before you. Yes? Yeah. Yeah. No, you see, our goal is not, I don't know what you mean by result. The result for us is not really, because again, the critical section is a piece of code. Well, how you use it? Yeah, you grab a lock, you execute some sequential code, and the semantics of its code is sequential. You're supposed to be the critical section should be run sequentially. Yeah, so you cannot have a situation where two processes running concurrently their critical sections. That's why we need this problem of mutual exclusion. Yeah. Yeah, well, actually, I'm coming to that. Yeah, so this is exactly what I want to show: the visibility graph of a solution of a mutual exclusion algorithm. Yeah. If you take a fix and execution, and in this particular execution, we say PI sees PJ, which means that the critical section of PI causally is causally preceded by the critical section of PJ. Yeah, PI sees PJ. PJ not necessarily see PI, but PI sees PJ, assuming that PJ was in the critical section before PI. Yeah, which means that PJ left critical section before PI started this critical section. Yeah, and we know that critical sections are totally ordered. In any execution, you don't have concurrent critical sections. Yeah, we have always a total order on this in this relation. So we can build. Well, not yet. I say we need total order, but it's not obvious yet. Yeah. So the claim is that in any canonical run of our system, yeah, for any Pi and J, at least one sees the other. Okay. Why? Well, because if it's not the case, then well, it means that Pi sees some Pk and Pj sees some Pk, but Pi and Pj are unrelated. What I can do, I can play with the order of steps, because there's no causality. I can order steps of Pi and Pj arbitrarily in such a way that they enter the critical section together, because they are not related to each other. None of them actually knows the other guy has left the critical section. So it's, well, it's again, I deliberately hand waving a little bit here, but if you think about it, spend some time, you realize that it's true. So because this is not the main point of this thing, so I should be careful with the timing. Okay. Okay. So it's just what I'm using here is the fact that the system is asynchronous. So the steps of individual processes can be permutated arbitrarily and still have an execution of my model. Right? So because the schedule, the only restriction I have is that some process never fails executing the protocol. So it never blocks forever. Because otherwise, if someone blocks, yeah, there's no future. Nobody can proceed. Yeah, because if you block in a critical section, nobody can access it. Okay, so what is the outline for me? Well, the idea here is that you try to first, you have three steps. The first step is you want to take the set of all possible executions of the algorithm and factor out some equivalence classes in this set. You just take some constructions and you get executions with specific orders of critical sections. Yeah, so for example, you take a permutation pi1 to pi n. This is a specific permutation of the set of processes p1 to pn, in which critical sections are accessed in this particular order. Okay. And well, I call it alpha pi. Yeah, this is a permutation. This is the execution I construct. However, it's not really, as we'll see, it's not really a specific execution. It's an equivalence class of executions, but it doesn't matter. Yeah, for encoding procedure and decoding, it's not important. It's a class of executions which are essentially the same. Now, specifically, in all executions in the class, the order of accesses to the critical section is exactly this pi. Okay. Okay, so what we did so far, we didn't do it, but this is what we are going to do. A set of classes of executions. Yeah, this is n factorial classes of executions. Yeah, in each class, the order of accesses to the critical section is fixed. Okay? What do we do next? We take an element in this class and we create a code word for it. Yeah, so this is what we call encoding. Yeah, so for each alpha pi, we produce a binary string e pi of length, and this is important, of length or of cost of alpha pi. Yeah, cost of alpha pi is the RMR complexity of this particular execution. You count all RMR operations in this execution. The length of the code word which you associate with this execution should not exceed this RMR complexity. Okay? And this is the trickiest part, actually. Because we need to look at the execution we constructed in the first step. We should look what are the RMRs executed there. And the code which we create shouldn't be too long. It should be bounded by the cost. Okay, otherwise it doesn't work. Okay? Finally, we created the code book. Yeah, this is the encoding part. Yeah, we need to prove that it's a code. Yeah, because otherwise maybe we created a set of strings which has no relation to what we created, so what is done by the algorithm. So we need decoding. So we should be able, given e pi, given a binary string in the code book, should be able to recreate alpha pi without knowing pi. Yeah, it's important. It's just a binary string here from some code book. Yeah, so we give an algorithm which takes this binary string and recreates the execution, which means that it's indeed a code. Yeah, so and now, yeah, since thanks to this, we know, right? We know that it's a code, and thanks to this, using Shannon's information theory, blah blah, this Shannon's argument, at least one string in this code book should have length n log n. Yeah. This is thanks to decoding step. And thanks to encoding step, the cost of some execution in this set of classes of execution should be at least n log n. Because we know that the cost, well, the length of the string in the code book is bounded by the cost of the execution. So we take this string in the code book which has length n log n, and we know that the corresponding execution should have a cost of n log n. Okay? Yes? Why different code words? Well, why should be distinct? Well, otherwise it's not a code. If you have two different executions which correspond to the same code word, it's not a code. Because if you don't encode these executions, you have confusion. You don't know. That's why you need this decoding step. Yeah, should be able, from each code word you need to decode a unique execution. A code is just a representation. It's just a way of describing something in zeros and ones. There's nothing special about it. Yeah, so you have some sophisticated thing which we call an execution. For each execution, we have a binary string. And for each binary string, we have a unique execution. It's a one-to-one mapping. Okay? Since you have n factorial executions, some binary representation should have length n log n. But it's important that the length of the string is lower than the cost. Okay? So this is what, so we construct from pi, we construct alpha pi. From alpha pi, we encode it to e pi. From e pi, we decode it to alpha pi. Yeah? E pi is the code of, which means that this is a code book for the set of classes we considered. Some code words have length n log n. The cost of some execution should be n log n. Yes? Could you say it again? No, we decode the run, and we come to that. It's a very good question, because you would say, yeah. So the question was, do we encode a permutation or an execution? And the answer is we encode an execution, because, well, one may say, oh, who cares? You see, for example, why don't we take this alpha pi as a sequence of solo executions? You have pi 1, pi n, so process pi 1 enters its criterion section, executes the critical section, leaves the critical section. Pi 2 does the same, pi 3, and so on. So there's no competition at all. Now let's think. Well, take the which algorithm we can take? We can take probably even the Peterson's algorithm. The cost of this algorithm, there's no contention. What is the cost of this algorithm? What is the total work in this algorithm? What do you think? It's n. It's well, you can tweak your algorithm in such a way that it's n. No, actually, I take it back. Peterson algorithm would still have n square, and probably even the Young and Anderson algorithm would have n log n. But you can tweak this algorithm in such a way that for this particular execution, it would be linear, would not be n log n. Why? What you can do is there's this thing which is called splitter. I don't know if you've heard of it. It's an abstraction coming. I'm sure you probably know this splitter things. It is from the old times. It's like it's very old, like very object, very simple. It's like the idea is that if there's no contention, these people don't compete, you pass it very quickly, and you have exclusive access to a resource. If there is some contention, some process writes to the objects you read, and so on, you can resort to the classical any mutual exclusion algorithm you want. But you have this short phase at the beginning where if there's no contention, I pass very quickly, which means that to enter the critical section, I have cost 1, constant. If there's no contention, if I let P1 run until it completes its exit session, the work of this process P1 is constant. For n processes, total work is n. Now, if we only consider executions of this kind for all permutations, what we get is we have a set of executions. In each execution, the cost is n. But still, if we encode it using these code words, some of the code words should have complexity n log n. So which means that we don't learn anything about the cost. So let me state it differently. It means that I cannot find an efficient encoding for any execution with this particular permutation. I need to find a specific execution with a lot of contention and what we call covering, maybe. such that the cost actually translates into the number of bits used in the encoding. Okay, maybe it sounds a bit confusing now, but think about it. Specific executions with certain order of critical sections may be very cheap. So the cost of mutual exclusion algorithm is actually coming from the fact, well, RMR cost in particular is coming from the fact that there is contention. People compete in their trying sections. So you, by identifying here, it's not a worst case construction. You don't care which execution is worst. Actually, you don't identify it. You don't construct it. What you show it that it exists, and that's it. And this worst case execution, which we just showed that it exists, is very likely the execution in which you have contention on the trying section. You have processes concurrently trying to compete for the resource. And this is the most difficult part actually here, the construction. Well, no, sorry, the construction. Well, the encoding, decoding is sort of follow-up, but construction is really non-trivial. Okay, and I'm not going to present it in detail because I need maybe another 3 hours just for this. But I hope you grasp the idea. See, unlike the previous approaches based on valency and covering, where you manually by hand construct a worst case execution, here you don't care. You look at the whole set of executions and you find a very interesting representation of this set using these code words. And just focus on this representation, prove something about this representation, or use what some other smart people proved before you. Yeah, specifically that the length of some string should be long enough. And then you deduce from this, you deduce the cost of some execution in the set. Okay? Similarly to what yesterday was discussed in the context of set agreement impossibility for Sperner lemma. You don't care which execution violates the condition. You know that it exists. Sperner lemma says that there is some execution in which all too many values are decided. Okay? Here's the same idea, just a different tool. Okay? I think I will. I think I did it. So what? I have half an hour. Yeah. Sorry. No, it's good. Good. I thought I spoke too long. So okay, construction. So what is the construction here? So I'm given a permutation. Pi is just a permutation. Yeah, it's just the order. So for this permutation, I need to construct alpha pi. Well, more precisely, I need to construct a class of equivalent executions, which I call alpha pi, in which critical sections are accessed in this order. Yeah. And I do it by iteration. So I begin with, well, it's sorry for the notation. Alpha 1 is a subset or subsequence of alpha pi of my resulting desired execution. So alpha 1 is an execution in which only p pi 1 executes. Just let him run through the whole protocol. Enter the critical section, leave the critical section. Okay? And then, again, induction, I have alpha I and alpha I plus 1. In alpha I, only processes from p pi 1 to p pi I participate. And now I introduce process p pi I plus 1. Okay, so how I do it? So what I do, I squeeze the steps of this guy as close to the beginning of the execution as possible. Yeah, so I don't run it at the end. I want to squeeze it somehow. I want to increase contention. Come back to this intuition that the more contention I have, the more cost is incurred. Yeah, the RMRs means that I spin on something and someone wrote to it, and I had to execute an RMR. Yeah, and the intuition, if nobody writes concurrently, there's no contention. So I want this guy to be there as much as possible, as long as it doesn't perturb the order of critical section accesses. Yeah, so in alpha I, processes p pi I to p pi I, p pi 1 to p pi I, executed their critical sections, finished them. Okay, so they're already in this particular order respecting pi. Now I introduce one more process, and I don't want them to execute the critical sections in a different order. I want them to stay the same, except that this guy should somehow create more, force them to do some more work or create. So this is, I'm not going to discuss it in detail because it's really, really technical. I really encourage you to look at the paper, but maybe not for this particular paper, but the follow-up paper, because this is probably not the best example of good writing. The idea is brilliant, but the writing can be better. So if you want to understand this in detail, go to the paper by Atiyah, Hender, and Wolfel, which was published later, and they use this proper encoding decoding, and they use the realistic model of cache coherence and DSM. Anyway, so this is intuitively the idea. So the trickiest part here is to maintain a set of what they call a meta steps. What is a meta step? A meta step is it's a set of read operations, set of write operations, and there is some winning write. So winning write is the guy who writes the last. And all these operations are on the same register. Okay, so it's like a step of a process, but a step of a group of processes on the same register. And typically in the meta step, you order first the write operations, then you put the winning step, the guy who writes the value, this is the value which is there, and then you order read operations. What can we say about the cost of the meta step? Well, if you have k processes in the meta step, the cost of a meta step is k. Why? Because every write counts as a unit of cost, and every read counts as a unit of cost. Why? Because they read something which has been just written. Yeah, so which means that there's no spinning. They have to fetch the value from the memory. Okay. So the size of the meta step, the number of processes in the meta step, every process executes exactly one step in the meta step. Well, not every, but there is a set of processes. Is exactly the length of the number of processes involved in it. Okay. And then what you do in every construction of this, from alpha to alpha I plus 1 and so on, alpha I to alpha plus 1. So what you do is you construct a partial order on these meta steps. So this mi is a set of meta steps, and then there is a partial order of meta steps. So it's not totally ordered. It's important again, so because you have some freedom of ordering steps which are unrelated, which do not affect the states of the processes. And you created it initially. Initially it's trivial. You have all meta steps here which are trivial. Just one process participates, and the partial order is total order if you just one process, obviously. And then you add one more process, and you get more and more sophisticated construction of meta steps. Okay, and we are going to use these meta steps for encoding because it's not. I said it for a reason. Yeah, why the cost of a meta step is proportional to the size of it. So it's important because that's exactly the number of bits which goes to the encoding. Yeah, so each meta step contributes exactly this number of bits to encoding. Okay. So this is what, when I reach stage n, where I used all my processes, I'm done. So this is essentially my execution. So my executions, the partial order of meta steps is a class of execution. It's not a specific, because if all meta steps are totally ordered, it means that okay, they precede one another. It's a fixed execution. But here I have a class of executions. Oh, sorry. But what's important for this class is that all executions in this class access the critical sections in the same order, and this is pi. Okay? So this is my construction. So now I have constructed for each order of, for each permutation pi, I constructed a class of executions. So now I need to encode them, to find the code word for each class. What is the code word? So here I start with, forget about alpha, now I start with this partially ordered set of meta steps. So this is what I said. I'm not going to really discuss in detail, but they use heavily the fact that it's a deterministic algorithm. So for each sequence of process identifiers, you have exactly the same state. And what they do, they create sort of a table of processes and the table of meta steps in which these processes participate. So one here means that this is the meta step in which P1 participates. 0 means it doesn't participate. So these are meta steps, this is participation. And what they do, they create a signature for each meta step, and the signature doesn't really give you the IDs of the processes because this would require too much information in the code. What they do is they count the number of writers, number of readers, and that's it, I think. So it's basically just something which is proportional to k, which means that it gives you k bits in the encoding, and that gives you the code word, which is asymptotically order of the number of the cost of the execution. So the encoding is kind of simple, but yeah, you might think, oh, don't you lose information by doing this? Yeah, how you reconstruct it then? Because you don't record the identifiers of the processes and everything. And this is the magic of this construction, and this is something which I'm not sure I can really explain you now. But the intuition is that again, you can look at the initial state and look, okay, who's poised on what registers? What are the meta steps enabled in this particular state? Given this, you can already deduce, well, by knowing the number of writers and number of readers in the meta step, you can deduce who are these writers and who are these readers. And this is what you use in the decoding. So you compute the minimal unexecuted step for each prefix of this encoding here. And this is how you construct the meta step composition. And I insist that it's not something which is easily explainable here in the class. But well, I guess we need maybe a couple of hours more just to focus on this and to understand this. But the intuition here again is that having this sophisticated class of executions with a lot of contention, with meta steps which contribute a lot to the complexity, you can represent this in a binary string where each meta step takes the proportional number of bits. Yeah. Knowing the protocol, now you need the knowledge of the protocol to reconstruct the execution. Knowing the protocol, you know for each prefix of the constructed executions, what are the enabled steps for each process. By looking at the code, you can see, okay, oh, look, there is a meta step which involves K1 writers and K1 readers. What could these writers and readers could be? I can look at the state of the protocol and I can deduce it unambiguously. Okay, so this is a little bit of magic, but it's very, very impressive. Yeah.
Could you please add more information about the deducing of some string into the composition of meta step? Because right now, for me, it looks like on the second step, we built a meta step of some steps to make some work and make a signature from it. And the third step, we try to do the same thing, but verifying that the previous step was correct.
No. You talk about decoding. This is the second step for you. Okay. So or encoding.
But steps, okay, because so they're connected to each other, right?
No. Okay. So you need to understand that decoding, you have no clue what pi is. The decoder doesn't know what is pi. If it knows, of course, the class of executions you need to construct. The decoding only gets a binary string. It's a code word in the book. You need to deduce the information about pi from this code. And the goal of the decoding step is to show that it is possible. So you don't confuse yourself. Having this binary string, you can unambiguously identify which execution this string corresponds to. Okay, so I write e pi from e pi to alpha pi because I want e pi to decode something which is alpha pi, but the decoder itself doesn't know pi.
Okay, I see.
Okay, doesn't make sense. Okay. Okay, so let me wrap up. So what did we learn so far? So we, first of all, not everything is computed in a distributed way. So whatever we can compute sequentially, there are some problems we are trivially computed sequentially, but not computed at all in a distributed environment. Yeah, so this is the first thing. Sometimes if we can't compute, the next question we should ask ourselves is, how much does it cost? Yeah. So of course you can say, my program is efficient as long as the user is happy, but sometimes it's not great. I mean, in some situations when the system is so heavily used, the user can be happy now, but maybe very unhappy in the future. And you will never know if you can optimize your program, unless you define a lower bound. Yeah, if you show that you define a lower bound and you found an algorithm that hits the lower bound, you can be sure that the algorithm is optimal. So if you want to make it more efficient, you need to change the program, or you need to change the model, but you cannot write a better algorithm. Okay. So there's argued that there are many lower bound results. Some of them we already discussed, from n log n, which we discussed for mutual exclusion, n square bit complexity for Byzantine agreement, all kinds of things. However, the number of techniques used to derive these lower bounds is bounded. So it's just a few tools. If you want to work in this area, you should master these tools. Even if you don't want to work in this area, I think it's a pleasure to master these tools. Anyway. So what we discussed is covering valency. We discussed information theory. There is a very nice class of work which we didn't discuss, which is based on potential functions. It's more like from the physics domain a little bit. So it's really interesting. You compute a function based on the execution prefix, and you show that this function grows when the prefix grows. So it's very interesting, and show that but you also know that the potential function is bounded and it grows, so which means that at some point it should hit the bound, and this is where your cost is achieved, for example. And well, combinatorial arguments, which I mentioned but I didn't use. There are some preliminary results using the simplicial complexes to say something about the complexity of the algorithm, specifically about round complexity for synchronous algorithm. Well, there is a very nice book by Atiyah and Faith Allen, Hagit Atiyah and Faith Allen, which is called Impossibility Results for Distributed Computing. And there are many lower bound examples in this book. Well, you should understand that lower bound and impossibility results are related. Yeah, what does it mean lower bound? Lower bound means that designing an algorithm with lower complexity is impossible. This is exactly what we are trying to show. Some open questions. Well, this gap is annoying. I think there is actually I should check, but I think this is already closed, but I'm not 100% sure. So this is the fact that perturbable objects and consensus require actually n registers, not n+1. We proved a lower bound of n+1, but the actual algorithms use n. I think this might be closed. I should check. I don't. Okay, so the time complexity for abstraction-free consensus still open. So we proved a lower bound on space, and there is a very strong suspicion that to complete an operation in the worst case in the abstraction-free consensus algorithm, you need n steps, but this is not yet proved. K-set consensus, yeah. So if you generalize consensus, instead of agreeing on one value, you want to agree on a set of values up to k. Yeah. Almost nothing is known. So the only anonymous case was explored, and there are some square root m over k for, well, m here is the level of abstraction freedom. So sometimes you want to show that you guarantee termination not when one process is running solo, but up to m processes running solo. So there's a generalization of abstraction free. So m abstraction freedom. So for n times m over k square root of this is a lower bound on space for k-set consensus in this model. No matching algorithm, just a lower bound. Similarly, you have, no, this is actually a tight lower bound, but for repeated instances of set consensus. So you're not solving one set consensus, but you run it over and over again. And for this, you have this tight lower bound, but it's kind of boring. However, you may say, oh, you never use consensus in isolation. You always use it repeatedly, for example, for state machine replication. But it's a hand wavy, so we still don't have a good result for one-shot set consensus. You can actually adapt to different things. You may adapt to the size of the system. Sometimes it's interesting to adapt to the contention. Yeah, so all these lower bounds are in terms of n, well, and k, which is this parameter of the problem, and m, which is a parameter of the model, you can also adapt to contention. How many processes concurrently are active? And build your lower bounds based on the contention. So it's a different question, different metric if you want. Well, it's other metrics, yeah, throughput. Yeah, maybe you can ask Vitaly about throughput. May tell you something interesting. So because for throughput is a tricky thing, you need to understand the workload. You need, because it's a cumulative metric. You need to understand which what is the stochastic model of your scheduler. Because otherwise, it's simply impossible to enumerate all possible executions and give worst case bound on throughput. This makes no sense probably. Non-volatile. So remember the recoverable compare and set algorithm which Danny described in the first class. Anybody can remember the memory overhead of this protocol with respect to just compare and swap, which is not recoverable? And square, because the idea was that you recover and you have no clue if your operation terminated or not. So you look for others to help you, to tell you if you succeeded, so that you could return true or false. And this of course requires n square, because you cannot allow different processes writing to the same location, because someone may see your older value and write to your location and overwrite the newer one, and you have no clue. Yeah, so that's why you have this dedicated registers for each process, telling the information to each other process. So just to implement, I don't know, a double word compare and swap in the recoverable way, you have n square overhead. And even worse than that, because if you remember, one of the assumptions of this protocol was that all written values are distinct. How you achieve it in practice, while you attach a sequence number, which grows without bound. Which means that not only you have n square memory locations extra in addition to your compare and swap variable, you also need these variables to be unbounded, to be able to store unbounded or very, very large numbers. Okay. So the question is it necessary? Is n square optimal complexity? Nobody knows. And actually, this whole domain of recoverable algorithms creates a new class of questions which we have no answer to. So I don't think there are any lower bounds proved so far. There are many algorithms, but no lower bounds. Okay. So the exercises. So this famous lemma 2, which I think is almost immediate. So the omega n space bound for deadlock-free mutual exclusion. Yeah. So okay. So now it's a space bound. It's not a total work bound, but space bound. It's actually a classical result. But it's very interesting to try to solve it yourself. Yeah. To show that you have linear, you require n registers, actually, exactly n registers to implement deadlock free mutual exclusion for n processes. Okay. And well, the total work for Peterson and n process algorithm for GSM and CC. It's also, I think it's a nice exercise to understand what these models are about. So this is all I put in the exercise PDF, so you can check. Well, these are basically the papers. There is a special document bibliography which lists all the papers. Some papers actually I uploaded also in this folder. You can look, and basically the 3 papers we discussed are there. The Gianti, Tan, and Toeg about perturbable objects, Lecky Zhu about consensus, and Fenn and Lynch about the total work for mutual exclusion. And I think this is it. So you have any questions? Anything you want to discuss right now? Yes? Without CAS, yeah. Well, actually, it's interesting. Well, we have a few minutes. So what's the answer? Yeah, for both. If you have CAS, why it doesn't help you? Yeah, let's take it offline. Yeah. The space complexity. Yeah. No, the space complexity, it's all read-write here. No, the exercise is all read-write, but it's an interesting question. What happens if you have CAS? But this was about the total work. If you have CAS, would it incur more RMRs in the canonical execution? And I think they claim that no, but I need to recollect why exactly. Yeah, so that's I cannot answer right now, but I think that's what they claimed in the paper, and I should look back in the paper to check it. From abstraction-free. Abstraction-free makes no sense for mutual exclusion because abstraction-free says from each configuration, if some process runs alone, it makes progress. Making progress in this context means entering the critical section, but you cannot guarantee that. No. There is a very interesting distinction of liveness of progress properties into blocking and non-blocking. So non-blocking properties, they guarantee some progress from any state. Blocking only guarantee progress under some conditions on the scheduler. Okay. So the mutual exclusion only works with blocking progress guarantees. Well, naturally. Okay, so before no more questions. Well, you can ask me a question. I just want to make one little. Just give me 1 second. Я перейду на русский, поскольку это касается в основном русскоговорящую часть нашей аудитории. So, если вы знакомы с этим человеком, он попал в беду, его семья нуждается в помощи, и в общем, если вам нужны детали, вы можете либо пойти на GoFundMe и помочь, либо обратиться ко мне. И даже если вы не знаете человека, все равно имеет смысл ему помочь. Это очень хороший человек, действительно, он очень сильно болен. Если у вас есть возможность, пожалуйста. Прошу прощения за не относящиеся к делу замечания. Вот. Так, секунду. Оп. Ну вот, наверное, на этом можно уже закончить. Спасибо.